So I'll give you some information to start off with, and then we'll get into that first example. So polynomials, I'm hoping you spent some time on polynomials last year. I'm hoping that you remember spending some time on polynomials last year. Do you know what the equation of a polynomial looks like? Y equals mx plus b is a polynomial. Yep. It's a linear polynomial. Polynomial, if it's written out in standard form, has a bunch of terms. The terms have powers on them and also have coefficients. And the powers are going to be integers, positive integers. So an example of a polynomial would be like y equals 7x to the third minus 2x squared plus 2x. That's a polynomial. But we will also be writing it in factored form. Oh, listen. So what I need you to know right now to start off on this example is that the zeros, and when we talk about zeros, this isn't strictly polynomials, it's any function. A zero is just an x value that make a function equal to zero. That's why it's called a zero. One of those times when I actually agree with the terminology. We'll get started on imaginary numbers. But zeros, that makes sense, right? If it makes the function equal to zero, it is a zero. Linking that back to something that we already know. There was something we did where we set a function equal to zero and solved. When did we do that? We were looking for what? X-intercepts, which means that zeros are X-intercepts. Kind of. Real zeros are X-intercepts. We'll get to that in a second. So a polynomial can look like this, or it can look like a bunch of factors multiplied together with powers on them. And that's how we're going to look at the first example. So I'm going to switch over to the second sheet here in a moment and see if you people are still writing some stuff down. Let me freeze this. Get it set up here. And again, I'm doing this on a separate piece of paper because we're going to do a whole bunch of stuff with this one equation. And you'll probably want to have it all together. All right, I'm going to go ahead and move on. I'll scan my notes and get them up on the canvas if you feel like you're missing something. All right, we're going to deal with this polynomial. Now, this is in factored form, and I have purposely spread my factors out because what we're going to do is make a little table underneath this and talk about how those different factors affect the zeros and then eventually how they affect the graph as well. So I'm leaving myself some space underneath each of those factors to write a little bit more information. That's why I've got it spaced out. All right, so this is in factored form. I got a quick challenge for you. If I were to multiply out all of these factors, we're not going to, because it would take a really long time and it would get really messy. But if I were, could you tell me what the first term in the standard form version of this polynomial would be? If I were to multiply all these factors out and turn it into a big long polynomial, could you tell me what the first term of that polynomial would be? Give it a shot. Go ahead, and if you think you know what it is, go ahead and write it down. So basically, I would end up multiplying the first term of each of these factors together. And if it's to the third power, like this one, this is going to get multiplied 3 times. So I've got x squared times another x. Now I'm up to x to the third. Times x, again, 3 more times. Now we're at x to the 6th. And then times 2x would be 2x to the 7th. 2x to the 7th plus ... We're not going to go through and find the rest of it. Not for this one. We will a little bit later, but not for that many factors. But we can agree that if we were to write out the polynomial, it would be 2x to the 7th would be the first term. Are we okay with how we got that? We'll come back to that in a moment when we talk about end behavior. But right now, let's talk about zeros. So those notes that we just took said that if something is a factor of a polynomial, then it's going to contribute a 0. So x is a factor of this polynomial. What is my 0 going to be if x is a factor? 0. What's my 0 going to be for the x minus 2? Positive 2. For the x plus 5, we're going to have negative 5. And for the 2x plus 1, we're going to have negative 1. What am I doing to get the zeros? Set the factor equal to 0 and solve. Set the factor equal to 0 and solve. So this negative 1/2 came from me thinking through 2x plus 1 equals 0. Oh, that means that 2x equals negative 1. Okay, so x equals negative 1/2. Are we okay with zeros? Let's talk multiplicity of these zeros. Multiplicity. Multiplicity is basically the number of times that that factor is included in the polynomial. And you can read multiplicity by the powers. So I would say a 0 of 0 has a multiplicity of 2. Because it came from a factor that was squared. Positive 2 has a multiplicity of 1. We don't have an exponent on there, but you know it would be a 1 if we needed to write one in. Negative 5 would have a multiplicity of 3. 2x plus 1 would have a multiplicity of 1. And if you were to add up all those multiplicities, what would you get? 7, which is the degree of the polynomial. That's not a coincidence. We'll get into a lot more with zeros and degrees and that kind of stuff next time. We'll be spending a few lessons on polynomials. All right, we're going to come back and add some more to this in a moment, but let's go back to our notes. Some other stuff down here. All right, so I need you to know that real zeros are x-intercepts. Real zeros are x-intercepts. It's trying to be an L. We say real zeros because it is possible to have imaginary zeros, but those do not cause x-intercepts on your graph. And for those x-intercepts, the multiplicity determines the behavior. Did you talk about your behavior of your x-intercepts last year in Algebra 2? Did you talk about whether it crosses the x-axis or whether it touches and bounces off the x-axis? Does that sound familiar to you at all? Did you use touch or bounce? Or cut or cross? It's kind of different. Cross and bounce? Okay. I think our book uses cross and bounce. Somewhere. So here's what I mean by this. If you have even multiplicity for a particular zero, that means you're going to touch or bounce off the x-axis. Some people use bounce instead of touch. So imagine that's my x-axis and I've got a polynomial and there's a zero right here. We know if there's a zero, it's going to cause an x-intercept, right? But if it's even multiplicity, that x-intercept is not, the graph is not going to cut through the x-axis, it's going to bounce off it at that point. Now, just because it's even doesn't mean it's going to be bouncing like that. It's possible that it could be coming up from below and bouncing off. But it's not going to cross over the x-axis. It's going to go right up to it, hit it, bounce off, and head the other direction. Where if it's an odd multiplicity, it's going to cross. So either go from positive to negative or vice versa. Does this sound familiar? Did you talk about this last year? And there's one more piece to this. Higher multiplicities flatten the graph. This is not very technical terminology, so let me show you what I mean by this. So if I had some intercepts, and I'm gonna make them all odd multiplicities. And since it's odd, that means we're crossing or touching. Crossing. If I had a multiplicity of 1, the graph's gonna cross through, and it's gonna cross through. If the multiplicity is 3, it's gonna cross it, but it's gonna kind of hesitate a little bit when it gets close to it. You'll see kind of a more S-shaped curve if it's multiplicity 3. If the multiplicity keeps bumping up, this is just going to flatten more and more and more. So multiplicity 5 is going to kind of flatten even more in that spot. Still going to cross, it's just kind of flattening out at that intercept. If I had a multiplicity of 2 versus a multiplicity of 10. Right, if I got a multiplicity of 2, that means we're going to be bouncing off. You'll see a nice, just kind of U-shaped bouncing right off. If we bump the multiplicity up, keep it even, but make it much higher, that graph at that intercept is really going to flatten out. You'll almost start to see it sort of squaring off. I'm going to jump back over to that example here and talk about x-intercepts and behavior at those x-intercepts in just a moment. Does anybody have any questions up to this point? You guys feeling all right about this? Is it kind of coming back? You guys probably spent a few weeks on polynomials, I'm guessing, last year. We'll spend a few lessons on it here. All right, let's go back to our amazing example here. So zeros lead us to x-intercepts. So my next row is going to be x-intercepts. And I'm color coding it the same color as zeros because they are related. Now, x-intercepts are points. So it's basically going to be the same information, but expressed as an ordered pair. So if 0 is a 0, then 0, 0 is an x-intercept. There's a lot of zeros. If 2 is a 0, then 2, 0 is an x-intercept. Okay, and let's also talk about our behavior at those intercepts. And for the behavior, we're either going to say cross or touch bounce, whichever you prefer, touch or bounce. So we're looking at multiplicity here. Notice that this first 0 has a multiplicity of 2, which means cross or bounce. Touch or bounce. So I'm expecting when we get around to graphing this in a moment, at the origin, this graph's going to come down and bump it and then shoot back up. Or maybe it'll be down below and it'll come up and touch it and go back down. Everything else here has odd multiplicity, which means at these intercepts, the graph should actually be crossing the x-axis. Going from one side of that x-axis to the other. All right, so we're going to go back to our notes. And then we'll come back to this one more time to wrap it up and graph it and see what it looks like. We'll have those graphing calculators out and ready to go here in a moment. Let's just talk really quickly about end behavior. I'm not going to be going over how to write end behavior and limit notation. We're just going to talk about what the graphs look like. It's my assumption right now that you know how to write end behavior with limit notation. Okay. So if you don't, go back and look at those notes or get my attention and I'll walk you through it. We're just going to talk about what end behavior looks like and the fact that end behaviors for polynomials be specific, not the same for every function, is determined by the sign and degree of the lead term. I'm going to make a little table for this. there's something that's going to be just really embarrassing for everyone. But we have to all participate because otherwise it's not. Okay. So I get that down and ask you to put your pencils down in a second. Ready? Gotta love this. This is great. It's good stuff. All right. This is hard for me to do because I got to do it backwards. All right. Can you take your left arm? Okay. Your left arm. You're gonna put your left arm down. Okay, pointing down, and your right arm pointing up. All right, like the disco dance move, right? All right. So right now you are an odd degree polynomial with a positive lead coefficient, right? Positively, and it's odd because you're going in opposite directions, right? Now, if I change your lead coefficient to a negative, what happens? Just flips over, right? So now it's negative. Flip it back, make it positive again. Flip it back, make it negative. Back, make it positive. All right, now make it an even degree with a positive coefficient. So now we're both going the same direction. Negative coefficient, positive coefficient. Awesome. You guys are great. Thank you for that. That wasn't as awkward as I thought it was going to be. So let's sketch this. So if it's an odd degree polynomial, it's going to be going down on the left-hand side and going up on the right-hand side. And some stuff's going to be going on inside here, some lumps and that kind of stuff. But remember, when we're talking end behavior, we are strictly looking at what's going on way out to the left and way out to the even degree, they're both going to be going up. If it's an even degree, they're always going to be heading in the same direction on the left and the right. And then when we change to a negative lead coefficient, it just flips it upside down. Too bad we didn't get that in before homecoming. Good dance with prom. There's still prom, right? And I gotta teach you asymptote dances still. So we should have a pretty solid routine by the time prom rolls around. All right. So going back to our example here. Going back to our example here, we need a degree. Well, we need a lead term. Oh, we did that. Oh, good. Right. We already worked out what the lead term is going to be. So that lead term is it's positive, and it has a degree of 7. So that's going to lead us to our end behavior. And I'm going to go ahead and make a little sketch of what the end behavior is going to look like. Positive odd degree. So I think we're going to be going up on the right, down on the left. Does that sound right to you guys? So let's do our end behavior and write it out. Try and do this on your own. If you get stuck and you've got to look up here for hints, that's fine. But see if you can write out that end behavior and limit notation. We called this f of x, so I'm just being consistent with what we called it in the original problem. So just by looking at the factors of this polynomial, we're able to determine quite a bit about it. I know what it's going to look like on the far left. It's going to be going down, and on the far right, it's going to be going up. I know I'm going to have x-intercepts, and there are going to be 4 different x-intercepts. 2 negative ones, 1 positive one, and then 1 at the origin. And this 1 at the origin, my graph's going to be bouncing off the x-axis at that point. The other 3, it should be crossing over the x-axis. So let's go ahead and put it into our calculators and see what it looks like. So we're going to be talking a bit today about setting a window on your calculator, and there's an art and a science to this. Fair warning, this is something that has caused some of my students in the past some trouble. So make sure you pay attention as we're talking about this. So I'm just going to go ahead and type this in as it appears in our original function. X plus 5. 2x plus 1. I'm going to graph it and hope to see what I'm hoping to see. Uh-oh. All right, that's interesting. Oh. So it's kind of a jumbled looking mess. All right, so here's what we're gonna, is everybody getting a graph that looks kind of like that? All right, so here's the thing. We need to set a window appropriately for this. I do not want you using the zoom out function. Okay, the only thing that you really ever want to use in the zoom menu is zoom standard. So zoom 6 will get you back to your standard zoom window. So I need to figure out, I know that I need to zoom out in my Y value. I can see my end behavior over here that I predicted. It is going down on the left and it is going up on the right. But there's clearly some big peak or hump happening here in between this x-intercept and this x-intercept. And I'm not seeing it because my graph doesn't go high enough. So I need to set a window that's going to go high enough. But how do I know other than just straight up guess and check? Please don't miss this, okay? Can you guys look up here and stop looking at your calculators? The way we're going to know is we're going to look at the table. Okay, I want to know how high does this graph go between -5 and -1/2. So I'm going to go second graph and look at my table, and I'm going to find -5, and -1/2 is pretty close to 0. And I can see here it's going to go pretty high. I see a Y value of 1800 here. Now there's a really good chance it actually goes higher than that. So when I go into my window setting, I'm going to set my Y max to, I don't know, I want to try 2000, see if that gets us there. Let's try 2000 and my Y scale to, I don't know, 100. And then graph it and see if we can actually see that peak now. We're cutting off a bunch of other stuff, but oh, hey, yeah, there it is. So we can't actually see that peak now. Now our graph definitely is dipping down below the y-axis over here between 0 and 1. So I'm going back into my table to look at what are my y values between 0 and 2. I'm seeing a y value that goes down to -648. Are you seeing 648 on your table also? Now chances are, again, it's probably going to go lower than that. So how far down do we want to go? -1000, maybe? Let's make it -1000 and see how that treats us. We'll see if it's cut off. If it's still cut off, then we'll bump it down a little bit. Not quite. Yeah, we're still cut off a little bit there. So let's send it down to oops, here we go. Negative, I don't know, probably 1200 would be enough, I'm gonna guess. We'll try it and see. It's not. No, oh no. 1300. I'll probably go 15 next. I'll go 15. All right. And okay, so there's an intercept. Now I'm kind of losing what's happening in the center here. So we'll come back and focus in on this in just a second. But we're able to see our peaks. Notice this intercept right here at -5. See how it is crossing the graph? Remember what I was saying about how the graph kind of flattens out if your multiplicity is a little bit higher? That came from this one that had a multiplicity of 3. That's why we're kind of seeing this little S shape here. This one at 2, see how it's just kind of crossing right over? It's not really making that S shape. That's because that was a multiplicity of 1. And it almost looks like it's just a single x-intercept here, but we know there's 2. They're just really close together. We'll zoom back in on that in a second. So why would we ever want to do this? Like if I ever asked you on a homework assignment or something to sketch and find your local mins and local maxes, that's why we want to get a good picture of this. So I'm going to make a sketch. In your homework, it'll say graph it in an appropriate window. When you graph it in an appropriate window, just make yourself a note of what your window settings were. Our window settings went from -10 to 10 on the x-axis. We didn't change those. We ended up going all the way down to -1500 on the y and up to, was it 2000? Yeah, up to 2000 on the y. You don't need to put a tick mark in there for every 1000 or anything like that. We knew we had an x-intercept at -5. 5. And there's one at 0, and there's one at -1/2, and there's one at 2. And I can see all of those on my graph. I can see the end behavior over here that we were anticipating, and that sort of wiggle as it crossed at -5. I'm basically just copying what I'm seeing on my graph at this point. And then it goes up, and it comes back down. I'm not too sure what's happening in the center there, so I'm gonna leave that blank. But I do see there's a lump down here, and then it comes back up there. And we're not going to pause right now to do this, but would you feel comfortable if I asked you to find me approximate coordinates for that local max and that local min that you can see on your graphing calculator? Second calc max and second calc min. All right, and if not, see me and I can help you out with that. Now, I could go into my calculator and zoom in to get a better look at what's happening right here, but I've got a pretty good idea what's going to happen. This is -1/2. And according to the table that you can see above your graph there, what's going to happen at that intercept? Are we going to be bouncing off at -1/2 or crossing? -1/2, we said we were going to cross the x-axis. So I know that this is going to come down. It's hard to see on the graphing calculator, but I know it's going to come down, and then it's going to have to swing back up to hit this intercept at 0, but we said it was going to bounce off at 0. So there would actually be another local min between there. And if I were going to try and find that, I would probably readjust my window so that I could zoom in a little bit closer to that and get a better picture of it. Okay. How are we feeling so far? That's probably like a couple of weeks worth of Algebra 2 review in like 25 minutes, right? Is it coming back though? All right. We're going to do a problem similar from start to finish all at once. This time I'm not going to give it to you in factor form, though. We're going to have to do a little work for it. It'll be fun work. Don't you worry. All right. So we are going to talk about zeros and multiplicity and intercepts and behavior. We're going to sketch. This time around, we're going to actually sketch it without using the graphing calculator. I'm going to sketch by hand. So here's our function. F of x equals x to the 4th minus 2x to the 3rd minus 35 x squared. All right, what do we know about this polynomial already just by looking at it? What can you tell me? Yeah. Fourth degree polynomial? And how's that going to affect the graph? I'm not too sure about what's going to happen as far as cutting or bouncing just yet, but what can we tell from that first term? Yeah. This is behavior, right? Up on both sides. Because this is positive, because it's an even degree, we're going to have an end behavior. It's going to look something like this. I don't know what's going to go on in between just yet, but I know it's going to be going up on the left and up. The other thing I could tell you by looking at this graph or this equation is I know where the y-intercept is going to be. Where's the y-intercept going to be? 0, yeah. To find the y-intercept for any function ever, you plug 0 in for x, and if we do that, we're going to lose everything. So it is going to go through the origin or touch the origin. I guess we'll find that out. Okay. Well, for the rest of this, we're going to need to factor this thing. So let's get started on that. We should have some pretty strong factoring skills, I'm hoping. I see a GCF here that we could pull out. That'd probably be my first step. Yeah, we got x squared that we can pull out of that. See what we got left after that. All right. Well, we've got one factor. We got a factor of x with a multiplicity of 2. Do you think this factors? Give it a try. If it doesn't, we're going to have to do the quadratic formula to figure out the other zeros. And that will happen from time to time, but I'm pretty sure this one does factor. Got to be x and x. 35 makes me think 5 and 7. Can you make 5 and 7 work? Which one needs to be negative? If we're going to add up to negative 2x, I think we want the 7 to be negative 5. Trick me on that. Whatever method you prefer. Xbox. If you are able to jump straight, I don't need to see you work for factor. Let's put it that way. So if you're able to look at it, use guess and check or some other mental method to factor, you're welcome to it. That Xbox thing is great. It works 100% of the time. You do the exact same thing every time, and 100% of the time it works. It just takes a lot longer for some problems. All right, I'd say we're fully factored there. So let's talk about zeros. I see 3 factors, so we should have 3 zeros. So equal to 0 and solve, so equal to 0 and solve, so equal to 0 and solve. Multiplicities, I'm just going to write them underneath it. You can write it next to it. This one was multiplicity 2 because it had a power of 2 on it. This one had a power of 1 instead of that one, so multiplicity 1 for the other ones. So we can write our x-intercepts and our behavior at those also now. So one of my x-intercepts is the origin, negative 5, 0, 7, 0. And then cross or bounce for each of those. Bounce, cross, cross. Yep, even multiplicity is going to cause you to bounce. Odd multiplicity is going to cause us to cross. I'd want to see, I think, key steps here. I'd want to see a factor. Zeros of multiplicity, yeah. If you didn't write this out, but you showed it in your graph, I suppose that's fine. Personally, I would write it out because, you know, brain science, like the more I interact with something, the longer I remember it. But yeah. All right, we're going to make a sketch of this. Now, when your homework asks you to graph it by hand, they're asking you to put the calculator down and do it by hand, okay? So I am not going to type this into my calculator and hit graph because I have enough information to make a pretty accurate sketch of what this thing is going to look like. So I'm going to get my X and Y axis set up, and I need to be able to go, it looks like in the X direction, as far out as -5 and +7. So I'm just going to take up some space here. This is going to take up most of the width of my paper. My hint to you when you do this is to go ahead and draw dots where your x-intercepts are. So draw those points. 1, 2, 0, 7. But then work your way from the end behavior in. Work your way from the outside in. So don't start with the intercept, start with the end behavior. So I'm going to start left or right. It doesn't really matter. I guess I'll start on the left. I know that my end behavior at the left edge of this graph is going to be heading up to infinity. I know that. We knew that right away as soon as we saw that first term. Now keep in mind, when you find these zeros, these x-intercepts, these are all of the zeros. They are the only zero. So it is impossible for my graph to come down and touch the x-axis anywhere between here and here. This is the first time it's ever going to see the x-axis. So from that end behavior, I'm going to make my way over to that x-intercept. And my question is, when I get there, am I going to cross over the x-axis and go down below it? Or am I going to bounce up and stay in the positive part? What are we going to do? We're going to cross. We said if this intercept, the -5, (0), that we're going to be crossing down below the x-axis because it had an odd multiplicity. So it crosses down below. Now, how far down does it travel? I have no idea, but that's not super important here. We're just trying to get a general shape of this thing. So somewhere in between here and here, it's going to have to spin around and start heading back up, right? Because it's got to get back to the x-axis at 0. And when it does return to that x-axis at 0, is it going to cross or bounce off? It's going to bounce off. And it's going to stay in the negative half of the graph. And again, as it travels over the right here, eventually it's going to have to bottom out and come back up because we got to make it up here for our last intercept at 7, which we said was going to cross. So that leaves us up in the positive territory, and that's good because we expected our end behavior to also be going up to positive infinity on the right-hand side of this graph. So that's what I'm looking for when it asks you to graph by hand. I want you to try and put the graph together on your own without using your calculator. Now, once you're done, of course, it would be smart to go ahead and type that in the calculator and see if you got anywhere remotely close to it. I don't know how far down these two lumps go. I don't know for sure that this one's lower than this one, but I've got a general idea what the graph's doing around the x-axis anyways. Any questions on that one? Yes.
You also want us to, like, when there's spots where
make the graph flatten the graph out a little bit, make it a little bit more S-like if it's crossing over. I'll be honest, this is not the type of problem that I will not, the test will be the test, and you'll be able to use the calculator on the whole thing. So I'm not going to force you to do this without a calculator on the test. However, I will tell you that if you, on the homework, if you want the easy way out, I guess you could just graph it on your calculator and draw it. right? But if you do this, if you participate in this mental exercise of trying to figure out what this is going to look like without looking at the graphing calculator, you're going to understand polynomials a lot better. And the stuff we're going to do with them when we get to rational functions is going to make a lot more sense to you. So I hope that you will. I hope that you will, when the instructions say sketch by hand or graph by hand, that you'll honor that and try your best. Now, of course, you get stuck, then graph it on your calculator and get yourself a little hints. All right. All right, we got a couple more things we got to cover here. We're doing good on time. All right. This next example, we're going to work backwards. I'm going to give you some zeros. So this is a polynomial function. I'm going to give you the zeros of the polynomial function. And you're going to build me a polynomial out of it. So the zeros for this one are going to be -6 and √5 and -√5. And our goal is going to be to write a polynomial in factored form and in standard form for this thing. And we're going to go ahead and assume that this is that these are all multiplicity ones. So how's your confidence going backwards? Do you feel right now that you can write an equation that has 3 factors that would correspond to those zeros? Going from factors to zeros, can we go from zeros back to factors? Yeah. All right. Looks something like that. Basically, we're just switching the signs on it, right? So that -6 would give you a factor of x plus 6. Positive √5 would give you x minus √5. Now, if I ask you for factored form, usually in a factored form, we don't like to have square roots. We're going to have to multiply all this stuff out at some point. My suggestion is let's go ahead and let's leave the x plus 6 alone for right now. Does anybody know the shortcut for this? Do you know that? Oh, good for you. A couple of you know the shortcut for multiplying 2 binomials where the only difference is one's a plus and one's a minus. You know that shortcut? Think about difference of squares when you're factoring a difference of squares. Conjugates, yes. So if I look at this, I'd say that's x squared minus 5. You could, of course, do FOIL or work it out with one of those rectangle things. But it's kind of the reverse of, like, if you were in algebra 1 and I asked you to factor x squared minus 36, you got really good at saying, oh, that's x plus 6 and x minus 6, right? This is kind of the same idea. I got x plus something, x minus something. It's just going to be x squared minus, and then multiply those two things together. All right. So we got that factor. That's all fine and good. That's still in factored form, though. Standard form here. We're going to have to multiply it out. You got no choice. However you want to do it, you can use FOIL. I like the little box thingy. Especially if I end up with anything like a trinomial or a 4-term polynomial. X cubed. Cool. Is that the only polynomial function that would have those 3 zeros with multiplicity of 1? How many others are there? An infinite number. Because what could I do with this original one with all these factors in it? What could I include in this that would not change the fact that the zeros are at those locations? What if I did this? Does that change the zeros? Nope. All that's going to do is stretch it vertically by a factor of 2, right? But the zeros are going to end up in the same spot. I could make it a -2, or I could make it a -2.2, or a -0.002. So there are an infinite number of polynomials that would work for this. This happens to be one of them. We will eventually do some curve fitting with this, where we won't know what this is. We'll call it A, and the way we'll find A is we'll write out as much as we can and then pick a point on that we know, plug it in for X and Y, and solve for A. But we'll get to all that later on. One last example for today, and this is all calculator. So we did one example where we did it kind of all on our own without the calculator. Let's do one with the calculator, where we've got to use some new functions. So for this one, we got f of x equals the opposite of x cubed plus 3x squared plus 7x minus 2. We're going to graph this and find our zeros. However, this one, I don't think we're going to be able to factor this one. So we're using a calculator for this. Now, there are a couple of things that I would expect you would know about this graph before you punch it in the calculator, right? Can you tell me about the end behavior? It's negative. Normally it would look like this, but it's negative. So, yeah. So we kind of know about the end behavior. I know that it's a third degree polynomial, so we might have 3 x-intercepts, no more than 3 x-intercepts. I know the y-intercept's at -2. That's about all I can tell you right now. Let's go ahead and type this in. Negative x to the third. Oops, let's clear that up. Now, you're going to have this instinct to just type in the equation and always hit the graph button. And sometimes you're going to hit the graph button. You're going to be like, oh, that's not what I expected. Because you forgot that you just did a problem where you changed the window to some wacky value. And so if you are hitting graph and you're seeing like, well, actually, that's not too bad. But you're kind of missing out on a lot of what's going on there. I see the end behavior that I'm looking for. But don't forget, our graph is still going all the way up to +2,000 and down to 1,500. Personally, every time I graph, I never hit the graph button. I always go zoom 6 because zoom 6 will always send you back to your -10 to +10. Hey, that looks better. That looks pretty good, actually. So go ahead and do zoom 6. Now, it's not perfect. I'm chopping off a little bit of this hump right here. So, I don't know. Let's look at the table. I'm going to estimate that. Well, that hump's definitely around like 2 or 3. Let's look at the table and see what our y values are when x is 2 or 3. Seeing 16 or 19. Maybe I'll make my y value, my y window go up to 25, just to be safe. Let's go 25. That still might be cut off, but yeah, that looks good. That looks good. Okay. Do you know how to find intercepts? Do you know how to make your calculator estimate intercepts for you? Do you remember where we would go to find these maxes and mins? It's in the same menu as that. So get yourself into there. That's that second calc menu, which is the trace button. And which one do you think we're going to use? Value 0, minimum, maximum. Intersect, not intersect. Max, we're going to go 0 for this because I'm looking for the x-intercepts, which are zeros, right? The x-intercepts are zeros. And when you do this, it's going to ask you the same questions before a left bound or right bound and a guess. So for your left bound, pick one of your intercepts, use your arrow keys to move your points. It'll still be on the graph, but make sure it's a little bit to the left of where your intercept is. We'll go there. And a little to the right. We'll go there. And then a guess. And hit enter. See if you can find that negative x-intercept for me. And let's write it down. So our zeros. I'm going to go 3 decimal places on this. Negative 1.726. Are you able to get negative 1.726 on your calculator? Please let me know if you're not getting that same number. All right, see if you can find the other two for me. Same method. Second calc 0. So we should be coming up to some numbers pretty close to that. Check to make sure you're able to get those. In a problem like this, you might be asked to find local maxes and local mins also. We've done it. Hey, by the way, I don't know if we've talked about this or not, but let's rehash just in case. My calculator, when I found this last intercept, I expected to say y equals 0, but it doesn't. It says y equals 1e negative 12. Do you guys know what your calculator means when it says 1e negative 12? What does it really say? It's saying times 10 to the negative 12. What it's really saying is that's like 0. That's basically 0, right? Because 1e negative 12 means take a 1 and move the decimal place 12 units, 12 places to the left. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 9. Anyways, there's going to be 11 zeros here. 9, 10, 11, decimal place 0. You're looking at that number right there. That's 0. That's as far as your calculator is concerned, that is 0. Okay, if you see something e with a negative, even like a negative 6, that's just your calculator is not perfect. There's small rounding errors that happen when it goes through these algorithms. You can rest assured that this is 0. Okay. Now, if you were working in NASA and you're trying to launch a rocket to hit Mars, moons, or something like that, that would not be 0. Right? That would be enough of an error to get somebody killed. But for our purposes, that's 0. Okay. That's our notes for today. If you had any questions about any of the stuff, especially the things that I told you, limit notation, that kind of stuff, let me know. Otherwise, once you get started on the homework assignments, we'll get it up on Canvas here. And I'll be around to check your homework. I do have time today. Hooray.